I'm Pete here, and I'm happy to have you during the summer months of August. You know that we've been interviewing top data engineers and data scientists, the leaders of open source data projects over the past few weeks. And today I'm excited to have Robert Nishihara here, who's the co-author of Ray and the co-founder of a new company called Anyscale. So Robert, welcome.
Thank you. Thank you.
Nice to have you here virtually. I see you're in San Francisco. I'm obviously in Jackson Hole, but with the wonders of Zoom, we're able to be here. And I'm not even sure if our socks are matching, but I think maybe that's the sign of the new era.
Yeah, that sounds right.
So, Robert, I've heard a lot about Ray. We actually had Joey Gonzalez speak to us maybe a year and a half ago or so on some of the research that was coming out of the Rise Lab at Berkeley. And it's been awesome to see that Ray is being supported by now a commercial entity that you've started. We won't talk too much about that unless there's aspects that you want to bring up. But specifically about Ray, the open source project, I'm really curious to hear the background there, how you got dragged into it. I know that you're one of these unique types who had a lot of internships at a lot of amazing tech companies while you were studying for your PhD. So you've had a interesting academic and commercial or a corporate past. But tell us a little bit about that and how you got into the Ray project.
For sure. Yeah. So when I started the PhD, I was focused on machine learning and machine learning theory, and actually, trying to design better algorithms for optimization and things like that. And one of the challenges that we ran into over and over, you have all these machine learning researchers who want to focus on machine learning algorithms and applications, but actually spend quite a bit of their time doing pretty low-level engineering to scale things up or speed things up. And so in order to test out your new machine learning algorithm, you may end up building quite a lot of infrastructure or scaffolding. And that's something we found ourselves doing repeatedly. And so we thought there had to be a better way. So, we began with a few of us building this open source project and really trying to build something useful. And since then, Ray has come a long way. We now have over 300 contributors and coming from around 100 different companies. And, the high level trend that Ray is trying to solve, the high level trend that we're, trying to address is just that distributed computing is really becoming the norm, that more and more applications, especially applications involving machine learning in some shape or form, need to run on clusters. And it's very difficult to do that. There's not a lot of great ways to scale up your Python applications or your machine learning applications, especially, and we can talk more about that. But so we were trying to make it really easy, trying to make distributed computing as easy as programming on your laptop, ideally.
Yeah, that makes sense. It's interesting that you talk about machine learning, but you also talk generically about distributed computing. Yeah. And I know this is one of the things that you like to emphasize about the Ray project, where in the beginning, I thought it was mostly for machine learning applications only, but I know that it's broader than that. Can you tell us a little bit more about that?
Yeah, that's a good point. I think to do machine learning well, or to really support machine learning well, you actually need a pretty general framework, because machine learning is not always something you do in isolation, where you just train a neural network or you just deploy your machine learning model in production, but rather it's often integrated into more complex applications where you might have data streaming in, you're processing the data in a streaming fashion, then you're taking those features that you're extracting and incrementally training new models, and then you're taking those models and deploying them in production and serving recommendations to users or things like that. And there are so many different moving parts. Machine learning is being integrated into so many different kinds of applications that in order to support machine learning applications well, you end up needing to be able to handle data. You need to handle serving. You need to handle streaming. All these different kinds of things. And so Ray is the ecosystem where like there's two layers to Ray. There's the core runtime, which if you look at the API, it's fairly low level and it's very general purpose. So it's basically the ability to take Python functions and Python classes and scale those up to run those in the cluster setting. And that's, so the API consists of tasks and actors. And we can talk more about that. So that has nothing to do with machine learning. But then with those primitives, we're building an ecosystem of libraries on top for scalable machine learning. And those libraries are primarily targeting scalable machine learning. And that includes things like training, hyperparameter search, reinforcement learning, serving, and so on. And there are actually a number of interesting, really cool third-party libraries that people are building that expand that ecosystem.
Got it. You mentioned already like scaling up Python. And so I thought that we could give you a chance to clarify and contrast Dask in a larger ecosystem. I'm sorry, Ray in a larger ecosystem. Dask often comes up, and so I'm curious as to how you compare and contrast the two.
Yeah, that's a great question, and this challenge of doing distributed Python or scaling up Python is just, it's a pain point for a lot of people, and there are a lot of really great projects that are trying to address that problem. And when I was actually an undergrad and first starting out in research and ran into this problem, this was a while back, I was using IPython Parallel, which is an earlier instantiation of this, and of course was really magical to use at the time. And before I talk about the differences between Dask and Ray, there's actually been a really interesting contribution that I came across in the past week or so, where someone in the community developed a thin layer that lets you 200 or 300 lines of code that lets you run Dask applications on top of Ray clusters. So essentially porting the Dask API to Ray, so you can actually use the Dask and Ray APIs they can interoperate within the same application pretty seamlessly, and that's pretty impressive. There was the fact that the fact that the author could do this in 200 or 300 lines of code suggests that's only because Dask has some really well designed abstractions, and this lets users take their the Dask data frame library or array library and run that on their Ray cluster. So that's sort of an interesting pretty cool thing that I came across recently. Now, so what's the difference between Ray and Dask? There's some pretty big, I would say, there are obviously a lot of architectural differences, but the one I would focus on is the API differences. So I mentioned Ray has tasks and actors, so it lets you take Python functions and Python classes and really, run those in the distributed setting. The Dask, I would say that the majority of Ray applications are really using Ray actors, and at its core, Ray is, the actor focus is a big part of Ray. How Ray works, and we that's important for us because we just wouldn't be able to support the kinds of applications that we are trying to support with training machine learning models or serving models in production or doing reinforcement learning. These kinds of things, we wouldn't be able to support them as easily without the actor abstraction. And so that's a huge focus for Ray. That's not and whereas the Dask API, the lower level Dask API is much more similar to the Ray task API for scaling up Python functions. So I think for users, that's probably a pretty important difference. And there are other smaller differences or maybe not smaller, but Ray is starting to support other languages like Java and C++ and things like that.
Got it. And a core component of Ray is that it allows for stateful processing.
That's right.
Talk about why that's so important.
Sorry, why is that important?
Mm-hmm.
Yeah. For a lot of well, when you're developing, if you forget about the distributed setting and you're just developing applications on your laptop using Python scripts, it's very natural to use not just Python functions, but also to use Python classes. And that's because logic that you're trying, the application logic you're trying to develop, there's often state, and that state needs to be encapsulated in classes, and that's a natural way to develop the applications. And the same is true in the distributed setting. The same kinds of applications, when you scale them up, they often still have state. That could be the state of a neural network, which is changing over time, like the weights of the neural network. That could be the state of some encapsulation of the state of the real world that you're interacting with. And there's sometimes, it's not that you can't do it without state. It's just that the natural way to write these applications is with classes.
Got it. So I just want to mention to the audience that we'll be taking questions for Robert in the chat window. So if you have questions that you want to interject into the conversation, we're happy to take those at any time. So feel free to sound off. So Robert, on that note, obviously both Spark and Ray come from research at Berkeley. Ray supports state, which is a key notion and sort of a key idea behind the platform. What are some of the other design principles that you followed? Like what did you optimize for when you were thinking about constructing Ray? And walk us through that process, if you don't mind.
Yeah, so the design principles that we care about for Ray are one, simplicity, and ease of use. And when I say, and the reason for this is that if distributed computing is quite complex. It's quite hard, right? It's conceptually, there's a lot going on, and our goal is to enable people who know Python to develop their applications and scale their applications without needing to be experts in distributed computing, right? So we really care about having a simple, intuitive API, because if you don't have that, then you can already do distributed computing just by using much lower level tools like TCP sockets and so on. But that doesn't, that's, of course, then you have to build a ton on top. So really making a simple, intuitive API is important for just allowing a much bigger audience to easily take advantage of distributed computing. So simplicity and ease of use is the first thing. The second thing is about generality. So we want to have a few, like I mentioned, simple APIs that are quite powerful and let you build a lot of things on top. So, if you look at and this is the advantage of having a lower level API. So if we provided a higher level API, like you can imagine a system like TensorFlow, the API is more around neural networks, right? And so if you're developing applications that do train neural networks, that's the perfect API to have. But if you were going to do data processing or stream processing or something, it's not the right API. And with Ray, we have a fairly low level API, it's functions and classes. So on top of that, you can they're quite general, so you can build a huge variety of different applications on top, in the same way that on your laptop you can build a ton of applications using functions and classes. So that we try to have a very flexible general API in addition to the simplicity. And then the third one is about performance. Like, it really needs to be fast, because performance is a key enabler for generality, right? If it's not fast enough, then there are going to be a ton of applications that you can't support, because those applications require that level of performance. And actually, this is one of the challenges with trying to design a very general purpose distributed system. If you support a variety of different applications, then you inherit the performance requirements of all those different applications, right? So, if some category of applications requires really low latency, and some other applications, require really high throughput or tasks or something like that, then your system has to support both of those things.
Got it.
So so simplicity and the ease of use, flexibility and performance.
Awesome. And so what about the architecture? Talk to us a little bit about the basic architecture of Ray and what we should expect there.
Yeah, so the architecture, that's a great question. it's actually evolved quite a bit it's gone through a number of iterations. And one thing we've done with Ray is we've rewritten it from scratch 3 or 4 times. There was actually, and with almost completely new code bases. There, and each time, it's gotten a lot better. There was an original prototype of Ray. The first prototype was built in Rust. The next iteration was using C++, and then we actually had for quite a while, we had a clean slate implementation in C. And more recently, it's then we switched back to C++ building on top of gRPC primarily, and then that architecture has lasted for a while, and we are also, that language choice has lasted for a while, but even within that choice, we sort of changed a lot of the concepts. So if you read the original Ray paper from, I think, 2018, some of the concepts have changed. But to say a little bit about how the architecture works, it's designed to avoid centralized bottlenecks. So whenever there are components like schedulers, that are sort of a logically centralized concept, we replicate those or shard those to avoid them actually becoming bottlenecks. And scheduling is a good example. So we actually run one scheduler on each machine in the Ray cluster. And then when workers on a given machine have tasks that they want to submit or want to run, they first talk to the scheduler on that machine. And then that scheduler might redirect them to another scheduler. But that's one of the key things for scalability. Ray is also really designed with performance and fault tolerance in mind. So on the performance side, one optimization I'll mention is the Ray object store, which actually this lets different worker processes on the same machine use shared memory to easily access the same data or the same objects without needing to create their own copies or without needing to duplicate the memory and do expensive serialization and deserialization. So heavily leveraging shared memory is really a pretty important performance optimization for a lot of for Ray, and a lot of machine learning applications heavily use numerical data, and so that comes up a lot. And then those are some of the things I would highlight. I guess with fault tolerance, it's designed in a way where you can imagine any process or any machine failing at any time, and that's something we want to things to continue working without any hiccups.
Got it. And so I know that you were inspired by some other frameworks and systems when you were thinking through how you wanted to design Ray. Talk to us about some of those and where your inspiration came from.
Well, there are a ton of different, I would say the biggest one there is we were in the RISE lab, right, the AMP lab, and surrounded by experts who had people who had built Spark, and also people who built Mesos and a number of other really successful projects. And that was immensely valuable, right? Because there are all these experts we were coming from more of a machine learning background, we were familiar with the machine learning applications that we wanted to run, but at the time we weren't, didn't have as much experience with distributed systems. So being able to learn from all that experience, was critical to being able to, it was really the perfect environment, this combination of people in machine learning and systems to be able to create this kind of project.
Yeah, that's great. What a benefit to being surrounded by some great visionaries and engineers in the space. I'm sure that was a real pleasure to work with some of those, and I know you've brought some of those on as advisors and co-founders to Anyscale as well. So congrats on that.
Yeah, it is. It is. It has been really fantastic.
So we have a question from Rick Lammers. Hey, Rick. Rick has a couple questions. One is, what's the recommended way to get starting with streaming data processing in Ray? Is there a specific approach that works best currently because of integrations or adapters that already exist?
Um, so the best way is probably to look at on the Ray in the Ray repository, the GitHub repository. There's a streaming directory, and that has some examples for how to how to do streaming on top of Ray. It's it's a bit it's still like experimental. It hasn't this particular library that's being developed. It's being used in production by some companies, but it's there's still some rough edges. So that's sort of the status there. But I think that's the best way to get started.
Okay, great. And since I want to transition into use cases anyway, he also has another question. You've had some incredible success in applying your framework to reinforcement learning. Will RL be the most important application area going forward?
Um, for Ray. So I think, reinforcement learning was a natural starting point because it's an example of something that's really hard to do with existing systems. Like if you want to do reinforcement learning on top of Spark or even TensorFlow or other systems, it's not really so easy to do that. And you actually, if you look at companies doing large scale reinforcement learning like OpenAI with their Dota project or DeepMind with AlphaGo and so on, they're typically building brand new distributed systems to run these applications. And so this is, we felt that reinforcement learning really highlights the need for a more general purpose distributed system. And that was something we could showcase, that you could do well with Ray. But from the start, and if you look at the API for Ray, it's something that, we intend this to be very general. We really think we want to make it easy to scale up Python applications to do distributed Python. And so that will be, reinforcement learning is still a focus for us, but it's not, but it's one of many different things we're trying to support well.
Gotcha. So the average Python engineer is a target user of Ray. Is that what I'm hearing from you?
That's right. Yeah. So, really, you can imagine someone they've developed. They weren't even thinking about distributed computing, right? They wrote their Python application, maybe as a hobby, maybe at their company, and they got the logic, to do what they wanted, but now it's too slow, or they need to, they want to scale it up. They need it to go faster, and they don't want to rewrite their application from scratch, and they don't want to think a lot about setting up infrastructure or building infrastructure for handling failures or fault tolerance or these kinds of things. They really just want to focus on their application logic and be able to not change the application logic much, but maybe and so we're trying to let them make a few changes, import Ray and so on, to be able to take advantage of all the to do distributed computing.
Great. So what are some other use cases for Ray, like besides the pinnacle reinforcement learning example that you gave and that you started with? What are some other practical use cases that you're seeing from the community now? Are there any commonalities, or are folks using it for one thing more than another, or how do you sort of size up how the community is using Ray currently?
I think a lot of the coolest applications are the ones that are integrating different kinds of computational patterns together, and that are things that to do without Ray, you would actually need to use multiple different distributed systems. So one example I alluded to earlier is, so one company has been building essentially like an online learning recommendation system where they have data streaming in from users, and they're processing this data in a streaming fashion to extract features. Then they're taking those features and training, they're incrementally updating recommendation models. and then they're deploying those models and serving recommendations back to the users, which then feeds back into the data collection. It's actually really, really impressive. The turnaround time for a data point coming in to a recommendation going out from a model that was trained using that data is around 5 minutes, which is much faster than the way these applications are typically architected. And so before before this whole thing is built on top of Ray, before using Ray, the way they did this was they had to actually stitch together 3 different distributed systems. They had one for stream processing, one for training, and one for serving. And so, and of course, that's on the more complex end of the spectrum in terms of what people are using Ray for. But, there are a lot of things that fall into that kind of category.
Oh, that's interesting that you cite a model serving use case. What's the general team overhead required to be able to get up and running on Ray? Like, what size of project is too small for someone to dive in?
You can have a single. It can be a single person. You don't need a large team to use Ray. It can start out with one person who came across the documentation, installed it on their laptop just with pip install Ray, and then started playing around with it just to try it out on their laptop. And the great thing there, and we do have some companies where there's essentially it was just one person started using it, and that was successful with it, and then expanded from there. I forgot what I was going to say. Let's see. Yeah, so there's some good examples of companies like that, and that's one of the things that people really say that they love about Ray is the fact that they often don't need to think about it that much at all, right? They start by developing their applications. They get their application logic to do what they want it to do without even thinking about scale that much. And then, after the fact, go in and try to scale it up. And it's typically, they don't have to re-architect it. They're often able to make fairly unintrusive changes, not always, but in a lot of cases. And that's something that's, that really simplifies the workflow, because you can just start with your application logic on your laptop, then import Ray and try to parallelize it across multiple cores on your laptop. And then once you've got that working, then the same code should run on, on a cluster.
And what sort of community support resources are there currently? I know you mentioned at the beginning of the conversation that there are hundreds of companies and contributors sort of all involved in the Ray ecosystem.
Yeah.
What's the best place for people to get support from that community?
So there are a bunch of different ways, but what we found has worked quite well is actually Slack. So we have a Slack that's open, that anyone can join, and there are different. It's a great way to people ask questions about bugs they're running into. They post errors. They ask questions about how to do certain things, or we discuss. We collaborate with different contributors there. We discuss plans about upcoming features and things like that.
Got it.
So that's been a really great way to interact with the Ray community. I mean, it's I wish we had started that earlier.
Well, I know you've also been super active in doing live stream events and digital events this year. So that's been great to see. And I noticed a lot of those recorded and are available on your website from community talks that you've been doing, I think, monthly on Ray. Is that right?
That's right. So there have been talks about, we've been doing online, essentially like mini conferences or meetups, and as well as tutorials where we're teaching people how to, use, there'll be one focused on like how to do hyperparameter tuning on Ray, or how to do machine learning operations on Ray, or and then there'll be talks about from different companies that are doing that.
And back to sort of the system and the way Ray works and fits in the ecosystem, like, are there specific tools that you see or systems that you see Ray replacing? I mean, we talked a lot about comparison and contrast with some of the other tools right now, but is there any like particular area where an engineer who uses X you think will get a big improvement from using Ray, or is that too specific of a question?
So no, that's fine. I mean, there are a couple different answers to that. So one is, I think the alternative to Ray is often building your own distributed system or building your own, and you might use tools like gRPC, and so really for people who, like, for example, all these companies or people building who were building like distributed systems to do reinforcement learning. Instead of having to build their own distributed system, we'd like to let these people really just focus on the application logic and not have to worry about the systems part. So that's the goal there. Yeah, I would say that's the main thing.
And so when you think about the roadmap of Ray, like, what are you particularly excited about that's coming up?
Yeah. So one conceptual thing that we are really focused on is the idea of, I'm sure you're familiar with serverless computing. And here I don't mean specifically AWS Lambdas. I mean the idea of letting people focus on their application logic and not have to worry about how the cluster scales up or scales down, or how many servers there are, or what runs on which machines. Really just letting the user think about the application and not have to be aware of all the different servers or what that configuration of, instance types, what that looks like. And it just, automatically chooses the right instance types, scales up and down as appropriate, and runs your application. And so making that work really seamlessly is something that, we're really excited about.
Neat. And I know you're listening to the community for feedback and trying to figure out like what to build next. Like, what's come out of the community so far? What are some other exciting things that you've seen built on top of Ray?
Yeah, so I mean, there are small things as well as big things. I think, one thing that we've started doing more recently, which we should have done ages ago, but is just really good support for typing in Python. And that's important for a number of reasons. It lets you obviously type check your applications, but also it lets you it gives better support for like autocomplete in IDEs and things like that. So that's one example. There's one really exciting thing. We've started to see a number of different third-party libraries choosing Ray to scale up those libraries, and I mentioned contributions like being able to run Dask data frames on top of Ray, or being able to starting to write. There are a bunch of natural language processing libraries that you can now start to you can scale up with Ray. So really trying to grow the ecosystem around Ray. That's been an important thing that people are interested in. Those are the ones that come to mind.
Okay, great.
Yeah.
I know that you have, for the community, keeping the community vein, I know that you have a Ray Summit coming up in September. That's exciting. Tell us about that.
Yeah, so this is something we want to provide an opportunity for more people in the community to really highlight to really see interesting industry use cases, and to really highlight some of these use cases. So there will be talks from a bunch of different companies showcasing how they're using Ray in production, or how they're using Ray to solve their problems. Also, a number of other libraries and in the ecosystem that are being scaled up using Ray. And there'll be a number of keynote speakers from who are high profile people in the Python community or machine learning community, and have a lot of interesting things to say about these topics. And so that's something we're super excited about. It's the best place to learn about how Ray is being used in industry. And yeah, it's a free conference. And so that's something we're really excited about.
That's really exciting. Well, we'll make sure to include the link in the chat, and we'll also mention that to our community as well. So that's yeah, congrats on launching that, and that'll be exciting to see develop over the years.
Thank you.
We have another question from Andrew. Hey, Andrew. Andrew's asking, what serverless abstractions are you evaluating and or using?
Yeah, so when I say serverless, it's actually the way you use Ray wouldn't change too much. So the API, like the way you develop applications with Ray would still be the same API. You're still taking your Python functions and Python classes and developing your application using Ray tasks and actors. So it's the same way for writing these Ray applications. It's just that now when you it will provide a way to run that, say on AWS or wherever, that automatically chooses the right instance types, that scales the cluster up and down appropriately, so you don't have to really make all these choices to configure the cluster and figure out the right way to set that up, or the right way to size the cluster.
Got it.
It's not changing the programming model. So we're not, AWS Lambdas has a pretty restrictive programming model, and so it's not, it wouldn't be coercing things into that form.
Okay. So Robert, this is a little bit of a change of direction, but I know we have lots of engineer founders in our community, and you and I are both engineers who have started companies. I'm just curious, like, what's the most surprising thing that you've learned being an engineer founder of something new?
That's a great question. I think, one thing that maybe it shouldn't be surprising, but as the company's growing and you have more and more people, the importance of having really great communication throughout the team and throughout the company, and making sure that the relevant people have all the relevant information and are and influencing all the relevant decisions. It's super important, and also not something that just comes for free out of the box.
Yeah, for sure. That's one thing I've learned, and this is a bit of an aside from a otherwise technical conversation, but it's important for us engineers to learn all the soft skills that are required to be a leader, to be a manager, to be a co-founder of a company. And those are things that sometimes we don't tend to learn when we're diving into docs and APIs and abstractions. And so finding a mentor, finding some help to learn how to be a better communicator and a better leader is something that I think there should be a textbook on. I've thought about writing it.
Maybe you should write it. Yeah.
But maybe that'll be a data council project that we'll do. That's a unabashedly non-technical thing, because I think a lot of us engineers would benefit from that as we want to continue to grow our careers and really impact the world and rally other people behind us as well.
Yeah.
Well, thanks for joining us, Robert. Really excited about your journey and the company. The Data Council community wants to support you however we can. So thanks for talking to us about Ray, and excited to have you here.
Yeah, thanks so much. It's been great chatting.
So I just wanted to mention to the community that we have other awesome things planned, even though it's the middle of August. We're not taking a summer break. So please join us next in 2 weeks, actually. We're going to have the authors of Apache Hudi on the show, Nishith and Vinod. And they're going to be talking to us about Apache Hudi and how to essentially enable transactional capabilities over your data lake. So that's going to be a super interesting show. That's in 2 weeks, Thursday, August 27th, at the same time and the same place. So thanks again for joining us. A reminder that we dropped a response form into the chat window. And so if you'd leave us a little bit of feedback, that would be awesome to know a little bit about what you thought about the show, what we can do better, what topics you're interested in hearing in the future, is always of interest to us. So thanks for joining us, everyone, and so long for now.